Hello everyone. Once again I welcome you all to MSP lecture series on interpretative spectroscopy. In my last lecture I started discussion on spin-spin splitting, and also the term I introduced is coupling constant. Let us continue from where I had stopped in my last lecture. So coupling constant, I had mentioned, it is very vital in understanding and elucidating the structures using NMR. And what one should remember is equivalent protons do not split each other. So that means usually protons present on the same carbon atom we are considering as equivalent, and they do not split each other, and especially methyl groups. And it's likely that in some cases where we have methylene, and if they are substituted with different on adjacent side, then there is a possibility of splitting each other. That arises when we have a second order situation. So as far as first order spectra are concerned, equivalent protons do not split each other. Protons bonded to the same carbon atom will split each other if they are not equivalent due to unsymmetrical nature of the molecule. As I had mentioned, the unsymmetry comes into the picture when they are differently substituted on both sides. Protons on adjacent carbon atoms normally will couple most of the time, unless they are separated by atoms such as oxygen or sulfur or chlorine, something like that, then they may not couple. But on other side, in general, protons on adjacent carbon atoms normally will couple. Okay. And protons separated by 4 or more bonds will not couple or show very weak coupling. So as long as they are fewer bonds apart, that means 1, 2, 3, or to an extent 4, they can show coupling. But if they are beyond that one, so they may or may not show any coupling. Even if they show coupling, 5 bond, 6 bond or something, that is very, very weak. Okay. So now let us consider one example of ethyl benzene and looking into the splitting pattern here. And of course here, while elucidating and understanding and interpreting the spectra, the symmetry comes very handy. For example, if you just look into the molecule, if you want to focus your attention on aromatic protons here, and you can see here, you can rotate this way. When you can rotate this way, basically what happens, you can rotate this through C2 axis. In that case, this one and this one are equivalent, and these two are equivalent, and this one is there. That means it should show 3 signals in its aromatic region in a ratio of 1:2:2. But on the other hand, this one would be very similar to what we come across in case of ethyl alcohol or chloroethane. We see here this one will be appearing as a triplet, and this one will be appearing as a quadret, and this will be overall, it will be a multiplet. So something like this it can show here. And then to make you familiar with splitting pattern, let me write again here how CH2 is getting quadrat here. So for example, here now we have 3 protons are there, and these 3 protons I am representing in this format, something like this. And then let us consider the situation 1 where all of them are aligned with the magnetic field. This is one situation, and the next situation is 1, 2 are, and then 1 is down. And now either possibility is 1 like this and down and 1 up. So the middle one is down, and the third case is this one is down and these 2 up. So these are the possibilities when we have 2 aligned and 1 opposing. And next, when we look into it, we can have 1 like this and 2 down, and then here I can write here, so 2 down like this and 1 here, or I can like 1 here, 1 here and 1 here. So these are the 3 possibilities. And then the third case is all of them are opposing the applied magnetic field. When they are applied magnetic field, so here it is shielded and here it is de-shielded. That's in the same order the peaks will appear, and this whatever the 4 peaks we are seeing here, you can see this is 1, 2, 3 are there, 3, 1, 2, 3 are there, and 1 and 1. So we will see here 1, 3, 3, 1. So this is how it comes, and same analogy holds good for identifying here 1:2:1. How that happens? Now CH2, as I mentioned here, both of them can be something like this, or 1 up, 1 down, or 1 down, 1 up, and then both of them are down. So here 1:2:1 we will see 1:2:1. So this is how we can calculate and look into relative intensities simply by doing this one. Of course, we cannot do for all of them. That's the reason we use Pascal triangle to identify the intensity of each line in a multiplet. Here I have shown the chemical shifts also. All of them are here multiplet with very low coupling between them, and you can see here this is 2.72 and this is 1.18 here. So now let's look into the splitting pattern for isopropyl groups here. And here we can anticipate three type of signals here. This one is not coupled, this may show a singlet, and this would be showing a septet 7, one is there, and of course I don't want to write here 7. You can calculate the intensity or look into the intensity by simply looking into the Pascal triangle, and the spectrum would look something like this. You can see here. So this one, if you see, this one is a singlet, it is appearing here, and then this one will be split by these two, n plus 1. This is 7 lines, and 7 lines will be there here. 1, 2, 3, 4, 5, 6, 7 will be there. And then these two will be split by this one, it shows a doublet here. And if you just look into carefully, this spacing is same as this spacing. This we call it as J. And then if you calculate here, 1, 2, 3, 3 J H coupling is what we are observing between these spaces. Okay, I have shown the expansion here. So you can see here, this is the expanded one, how nicely 1, 2, 3, 4, 5, 6, 7 lines are here. So now distance between the peaks of multiplet measured in hertz. Whatever the distance I showed you, that we call it as coupling constant, this is always measured in hertz. And then they are independent of strength of the external field. Again, when we measure the coupling constant in hertz, they are independent of strength of the external field. The external field, if you term it as B naught, they are independent of external field. Similarly, chemical shifts, when they are presented in ppm, they are independent of strength of the external field. So multiplets with the same coupling constants may come from adjacent groups of protons that split each other. I repeat again, multiplets with the same coupling constants may come from adjacent groups of protons that split each other. So now let's look into coupling constant values for different types of molecules. You can see here 1, 2, 3 bond coupling is there, and then this is around 7 hertz, and then here 1, 2, 3 bond coupling is there, and between we have a double bond, so it is 10 hertz for cis. And when we have trans, that means magnitude of trans coupling is more than the magnitude of cis coupling. You can see here cis coupling is 10 hertz, whereas trans coupling is 15 hertz. And the geminal, if there is any non-equivalence is there and the substitution, in that case what happens, you can observe very small coupling between the hydrogen atoms present on the same carbon. This we call it as geminal coupling. This geminal coupling is very low. And then in case of aromatic groups, this orthoproton coupling will be in the order of 8 hertz, and then meta will be 1, 2, 3, 4 bonds. Here 1, 2, 3 bonds. This is 3J, and then here 1, 2, 3, 4 bond, 4J, it is 2 hertz. And then in case of allylic, what we have is 1, 2, 3, this is around 6 hertz. So some of these things one should remember, or by repeatedly interpreting the spectra of several organic molecules, you will be knowing exactly where the coupling constant value would come, what is the magnitude of the coupling constant. In absence of free rotation due to steric hindrance by a ring or bulky groups, splitting and coupling constant values may vary. Again, you cannot really set this as a standard value. It can also vary due to free rotations or due to steric hindrance by ring or bulky groups, because coupling constants are often conformation sensitive. So now let us look into complex splitting. Let us consider styrene molecule. If you look into styrene molecule, okay, these 3 protons are there. They are designated as HA, HB and HC. If you look into molecule, this is unsymmetrically substituted because HA is cis to Hc whereas trans to Hb. As a result, what happens? These two appear to be chemically equivalent, no doubt, but they are not magnetically equivalent. So that means when two nuclei or two hydrogen atoms on same carbon atom are chemically equivalent but they are not magnetically equivalent, then we come across complex splitting. But let us consider assuming this is a first order spectrum. In this case, what happens? You can see signals may be split by adjacent protons different from each other with different coupling constants. Example, Ha of styrene is split by adjacent Hb trans to it, because first it should be split by trans because trans coupling is larger. You know that it's 17 Hertz and it is 11 Hertz. Then it will be further, the lines further split by a trans, that means Hc proton. How that can be shown? You can see here the spectra is given here, and then values are also given here. This comes around 5.25 and this comes around 5.76 and this comes around 6.72, and all aromatic protons are coming around 7.3 to 7.4. And then interestingly, if you see here, although it appears like a doublet, it's actually a doublet of doublet. Same thing is true in case of this one. This is also doublet of doublet, and this you can clearly see it's also a doublet of doublet. That means 4 lines are there, and here also 4 lines are there, and here also 4 lines are there, but spacings are a little smaller. So how that's happening, you can clearly see here. Let us first consider Ha. Ha, we have the chemical shift of 6.60. First, it is Ha is split by Hp because the magnitude of transcoupling is more. It first splits that into doublet. The separation is 17 Hertz here. Then each line in the doublet is further split into doublets because of coupling with cis coupling, that is in the magnitude of 11 Hertz. Now, at the end, what we are getting is doublet of, this is called as doublet of doublets. The Ha multiplied would be called as doublet of doublets. And similarly, when we look into Hb, Hb again, first it is split by Ha because it's a trans coupling, magnitude is more, and now Hp is further split by Hc present on the same carbon atom because they are no longer equivalent. So there is some non-equivalency is there. As a result, they split each other. As I mentioned, this is called geminal coupling, and geminal coupling values are of the order of 2 or less. So here what we are getting is BC coupling is about 1.4 Hertz. That's the reason you can see in the spectrum, we saw the spacing between 2 lines is very narrow. So now let's consider into Hc, and in Hc if we consider the larger coupling is only cis coupling, Ha-Hc, that is 11 Hertz, first splits into a doublet, and again each line in Hc in this one will be further split into doublet, and the magnitude of this BC is same what we came across here. So this is 1.4 Hertz. That means this is also a doublet of doublets, this is also a doublet of doublets, this is also doublet of doublets, and so as a result what we see is in this portion styrene olefinic region, what we are seeing is 4 signals, each one is having 4 lines. That 4 lines can be designated as a doublet of doublets, doublet of doublets, and doublet of doublets. So this is what we saw in the spectrum here, you can see here. So this is all doublet of doublets here. Now let's look into another example here. In this one, chemical shift values are given here. This is 1.63, a doublet is there because this is coupled with this one. These two coupling is there. And next 3.52, 3.52 here it is there. And this is coupled with this one, and then 3.78 again, 3.78 here, and then what we have is 4.10 we have here. So now you can see the number of lines. You should be able to tell what are the couplings involved in those things. Okay, you try to work out. If it's not possible, we will solve that one again. Now let's look into another aspect while determining the coupling constant is stereochemical non-equivalence. So what is this stereochemical non-equivalence? In general, 2 protons on the same carbon atom are equivalent and do not split each other. So I gave emphasis about that one, that no geminal coupling as long as the protons or hydrogen atoms on the same carbon atoms are equivalent. But that is not the case in case of styrene, because styrene, if you just look into it, I showed you HA is coupled, is having trans relationship with one HB, whereas it has cis relationship with HC. As a result, what happens? The entire molecule is not symmetrical. As a result, what happens? You observe geminal coupling. So if the replacement of each of the protons of a CH2 group with an imaginary Z gives stereoisomers, then the geminal protons becomes non-equivalent and will split each other. That's what exactly happened in case of styrene molecule. So molecules having non-equivalent geminal protons, I am showing you here few examples. In this one, you can see HA and HB are on the same carbon atoms, but they are non-equivalent, and you can anticipate coupling between HA and HB. They are geminal protons. And same thing is true in case of styrene also. So HB and HC are geminal and they are non-equivalent, and you can anticipate coupling between them. But however, the magnitude of this coupling is very small. Okay. Same thing is true in case of this one also. You can see here D and C. So geminal coupling is observed here. So now the time dependence. So what is the time dependence? Molecules are tumbling relative to the magnetic field. So NMR is an average spectrum of the all orientations. If you recall, when we placed H2 and F2 molecules perpendicular to the magnetic field and parallel to the magnetic field, these are the average orientations considered, taking average of all possible orientations. That means the molecules will be tumbling relative to the magnetic field. So NMR is an average spectrum of all the orientations. That's the reason we do spinning. Axial and equatorial protons on cyclohexane interconvert so rapidly that they give a single signal. At room temperature, if you record NMR spectrum for cyclohexane, they interconvert axial and equatorial, although we can differentiate them, but the exchange or interconversion of axial to equatorial is much faster than the NMR time scale of 10 to the minus 9 seconds. As a result, what happens? We get a single signal. So proton transfers for OH and NH may occur so quickly that the proton is not split by adjacent protons in the molecule. Again, same thing happens. The exchange happens when we have groups such as OH and NH in a molecule, and the exchange is so rapid that basically what happens, we don't see any splitting due to the presence of OH or NH on adjacent protons. Now let's look into hydroxyl proton here. I have considered ethyl alcohol here, and if you consider ultra pure samples of ethanol, it shows splitting. Ultra pure sample of ethanol, if you record quickly NMR, it can show splitting of methylene due to OH as well. For example, you can clearly see here, this is a triplet for methyl because of split by 2 methylene protons here, and then this will be split into quadrate, and each line in the quadrate is further split into a doublet because of HO, and HO again split by this one into a triplet. This is a very interesting one, not often you come across. Very clearly you can see here. So basically first it splits into quadrate. This is 1:3:3:1, and each one is split into doublet. Then it would appear something like this. Okay. So this is what we are seeing in case of CH2 here, and of course here in this case what happens, this will split this one into a triplet here. But ethanol with a small amount of acidic or basic impurities will not show this splitting. This splitting due to OH vanishes with a small amount of acidic or basic impurities. So now if you see here in this one, it is not pure. As a result, that splitting whatever we saw is disappearing here. So OH will show only one signal here, and CH2 shows as usual quadrate, and CH3C shows a triplet here. So how about NH protons? So moderate rate of exchange is observed when we have NH protons. Peak may be broad. Okay. You can see here this compound, we have here CH3 is there here, and CH2 is a quadrate here, and then this NH2 is showing a very small broad peak here. So this is how most of the time we observe for OH and NH or NH2 peaks in the NMR spectrum. So identifying the OH or NH peaks, how to do that one? Chemical shifts will depend on concentration and solvent. To verify that a particular peak is due to OH or NH, shake the sample with the D2O. For example, because of difference in concentration, we may not, or exchange, we may not see signals due to OH and NH, or in the beginning we see it, and then to confirm that one, what one should do is keep the solution in D2O for 24 hours and then record, and then if the peaks due to OH or NH disappears, that confirms that OH or NH is there. Deuterium will exchange with OH or NH protons. Okay. On a second NMR spectrum, the peak will be absent or much less intense. So you take NMR for the freshly prepared solution and then keep it in D2O overnight and take it, and if the peak disappears, that confirms that they are due to either OH or NH. Let me stop here and continue more discussion on coupling constant and type of spectra we come across in my next lecture. Until then, have an excellent time. Thank you.